This is Rubber Expansion Joints, Basic Applications to Advanced Solutions, a two-part webinar. The first part today will focus on system design and optimization. I would like to thank the Hydraulic Institute for giving me this opportunity to validate the importance of rubber expansion joints in pump piping systems. Now, rubber expansion joints may not be the most complicated component in a pump piping system, but it is often misunderstood and misapplied. I will try to identify areas of misunderstanding and misapplication throughout this presentation and hope you find it informative. System design and optimization. Owners and pump pipe engineers desire greater system optimization that include higher reliability, improved energy efficiency, a smaller system footprint, lower construction cost, modular construction, and with less structural support. Utilizing performance rubber expansion joints, we're going to abbreviate REJs, can achieve these goals by reducing the need for cumbersome main anchors, numerous guides, and/or rigid pipe loops. Functionally, this is achieved with the rubber expansion joint's ability to accept damaging nozzle loads and pipe stresses, and replace them with the rubber expansion joint's low stiffness and high movement capability. So that is the function of the rubber expansion joint, and it is not very complicated. And if it was not often misunderstood and misapplied, we could end this presentation here, making it the shortest webinar in HI history. But they are misunderstood, so we will continue. A good way to continue is to ask, what are the sources of nozzle loads and pipe stresses? They include installation misalignment pipe strain, thermal expansion and contraction reaction forces, shock and vibration loads, ground settlement and other external displacement forces, and pressure thrust forces. Installation misalignment pipe strain. We can visualize this, and if the misalignment is small or the piping is flexible in the direction of misalignment, the loads and stresses may be low. If the misalignment is large and the piping is rigid, then most certainly the loads and stresses will be high. Rubber expansion joints absorb misalignment. Again, we can visualize thermal expansion and contraction reaction forces. If the thermal movement is small or the piping is flexible in the direction of thermal movement, the loads and stresses may be low. If the thermal movements are large and the piping is rigid, then most certainly the loads and stresses will be high. Rubber expansion joints absorb thermal movements. Shock and vibration loads. If the piping is flexible and not in resonance with the vibration source, the loads and stresses may be low. If the piping is rigid and is in resonance with the vibration source, then most certainly the loads and stresses will be high. Rubber expansion joints absorb shock and vibration. Once again, we can visualize external displacement forces. This includes ground settlement, seismic events, wind and snow loading, to name a few. If the displacement is small and the piping is flexible in the direction of displacement, the loads and stresses may be low. If the displacement is large and the piping is rigid, then most certainly the loads and stresses will be high. Rubber expansion joints absorb piping displacements. Pressure thrust forces. Many rubber expansion joint arrangements will exert a pressure thrust force axially on the piping system that must be restrained. Restraint is accomplished by either designing the piping system with main anchors and numerous guides, or utilizing control units installed in a tied configuration, tie rods, on the rubber expansion joint. It is important to understand that when tie rods are utilized, With conventional rubber expansion joints, they can no longer absorb axial movement. This is the #1 misunderstood aspect of rubber expansion joints. Some associate this force, the pressure thrust force, with the larger area of the rubber expansion joint versus the pipe diameter, as shown in the illustration on the top right. That may contribute to an increased force, but not the majority of the force itself. The total force is a result of introducing the flexible connector in what otherwise would be a rigid piping system. Rigid piping is comfortable carrying a great deal of pressure thrust force as a tension load in the pipe itself. Once you introduce the flexible connector, it can no longer do so, and the load is now a compression load on the ends that must be restrained with main anchors. So, is any one source of loads or stresses more damaging than another? No, and each source independently has the potential to exceed allowable nozzle loads and/or pipe stresses. Protecting the system and essential equipment from some but not all damaging sources is not acceptable and equates to errors of omission. Rubber expansion joint features and benefits include absorb large all-directional movement, reduce noise and vibration, has a cycle life in the tens of millions, compensate for misalignment, provide access to piping and equipment, relieve pipe and anchor stresses, have superior chemical and abrasion resistance. Again, not very complicated, but often misapplied and misunderstood. We show alternative pipe solutions to illustrate different applications and to improve understanding. The example application is of a 36-inch diameter pipe, 100 feet long, carrying 90 psi of pressure. It's carbon steel with an anticipated change in temperature of 100 degrees, and that translates to an axial movement, thermal expansion or contraction of 0.8 inches. Solution 1 is a common application utilizing unrestrained rubber expansion joints. This approach has a pressure thrust force component that must be restrained. End loads are calculated as the sum of the pressure thrust force and the rubber expansion joint spring rates and extends to 92.2 thousand pounds of force. This is an effective solution, but it is understandable why a pump manufacturer would not want their equipment to be treated as a main anchor. Solution 2 is a common application utilizing a rigid pipe loop. This approach exerts zero pressure thrust force on the ends, but has a sizable pipe strain component. The pipe strain, while is within allowable pipe stresses, is still a large force, 105,000 pounds in this case. A pump manufacturer should be equally concerned that this large force is not exerted on their equipment. Solution 3 utilizes an advanced restrained rubber expansion joint, an inline pressure balance that takes both the pressure thrust force and pipe strain components out. The end loads extended are solely the stiffness of or spring rate of the rubber expansion joint. 4,500 pounds, in this case, a very manageable load. Solution 4 utilizes universal tied rubber expansion joints in a flexible pipe loop configuration that also takes out both the pressure thrust force and pipe strain components. The end loads extended are solely the stiffness of the spring rates of the rubber expansion joints. However, a change in pipe direction must be utilized. A low 2,100 pounds of force is calculated in this case, a very low force. Rubber expansion joint size and performance range. They can be manufactured from 1 inch to 144 inch. Pressure rating over 300 psi. Temperature rating up to 400 degrees Fahrenheit. Large all-directional movement with low spring rates. So what is a performance rubber expansion joint? It utilizes tire cord and a bias ply to optimize directional strength and number of plies. Performance benefits include reduced body thickness and weight, greater movements, lower stiffness, that's spring rates, larger flange sealing area. Additionally, tire cord is coated with a resorcinol formaldehyde latex, RFL, developed by the tire industry to prevent delamination. Unrestrained rubber expansion joints take common configurations: a single wide arch with large all-directional movement and low spring rate or stiffness. You can have a double or two wide arch with twice the movement and half the spring rate. A triple or three wide arch has triple the movement and 1/3 the spring rate. Quadruple, four wide arch has quadruple the movement and 1/4 the spring rate. So there are two design elements in play here. If the piping needs the movement capability of a 3-arch expansion joint, for example, you would select it. If it needs the movement capability of a single arch, but also needs the spring rate or end loads of that of a 3-arch, you would select the 3-arch joint. Control units can be utilized as limit rods with a gap or tie rods, no gap, depending on the application. They are designed for the internal pressure thrust force of the system and can be attached to the external or internal hardware of the expansion joint. The arrangement may include a combination of rubber grommets, flat or spherical washers, as well as internal limits for specific applications. Completely versatile, reducer rubber expansion joints are an economical way of combining a reducing pipe fitting with an expansion joint. Additionally, the center line of the two different integral flanges can be manufactured as concentric, eccentric, or to a custom offset. Completely versatile continues with a lightweight or low pressure design rubber expansion joints, and they are designed with fewer layers to facilitate greater movement and lower spring rates. High pressure rubber expansion joints are designed with additional layers of high strength tire cord and high tensile steel reinforcement. High temperature rubber expansion joints are designed with a high temperature resistant EPDM or Viton leak-proof tube and seamless cover with Kevlar high temperature and high strength tire cord reinforcement. Completely versatile continues with lateral and angular offset rubber expansion joints, and they are designed with built-in lateral and angular offsets respectively to accommodate non-standard field conditions. They provide ease of installation without compromising any of the performance capabilities of the rubber expansion joint. Restraint rubber expansion joints include universal tied, hinged, and gimbal. We will describe these rubber expansion joint types more in an upcoming applications section. Advanced restraint rubber expansion joints include inline pressure balance, elbow pressure balance, and dismantling rubber expansion joints. So these are the most common rubber expansion joint types that can be used. We get into now the pipe optimization process. So what is the pipe optimization process? A systematic and sometimes iterative approach for the selection and application of rubber expansion joints that include dividing the proposed piping into individual sections, i.e. straight runs, L or Z-shaped bends, by choosing tentative anchor locations. Each section can then be optimized and later rejoined with the complete piping system. This is more a simplification process than an actual design process, but it helps greatly. The process will require additional pipe design consideration for capabilities and limitations of different anchor types, including main, directional, and intermediate, pipe codes, including ASME B31.1 and B31.3, and standards, including ANSI HI 9.6.2 and 9.6.6, location of various equipment, branch connections, and space restrictions, as well as available support structure and load limitations on piping and equipment, operating conditions, including but not limited to temperature and pressure, amount of thermal and/or external movement anticipated, need to absorb noise and vibration as well as compensate for misalignment, need to provide access to piping and equipment, need to absorb shock loads and required cycle life, and capability and limitation of different rubber expansion joint designs, including unrestrained and restrained arrangement. Seems like a lot, but it's repetitive and it's a good checklist for what the design process requires. An application for unrestrained rubber expansion joints. Unrestrained rubber expansion joints represent the simplest and most cost-effective solution for absorbing axial movement in piping systems equipped with main anchors and numerous guides at specific spacing. No control units are required in this application. For absorbing lateral movement, a directional main anchor may be used. Common features and benefits of rubber expansion joints are achieved. Unrestrained expansion joints provide the above given the support structure and adjacent equipment do not have load limitations. That's another way of saying the pump manufacturer refuses to let you use their pump as a main anchor. The economic benefit of this approach over rigid pipe loops include a smaller footprint and improved energy efficiency. So this is a typical arrangement. You would see two main anchors, a long length of axial pipe, numerous guides at specific spacing, and control units can be used as limit rods for secondary restraint or as tie rods when the support structure and adjacent equipment have load limitations. Functionally, the axial movement of the long length of pipe is directly accepted by the expansion joint. Again, the main anchor is needed to restrain the pressure thrust force. But the thermal movements axially can be done tens of thousands of times. Application: restrained rubber expansion joints. Restrained rubber expansion joints can be used to absorb all directional pipe movement while restraining pressure thrust forces and other external loads. The pressure thrust forces in these designs are often self-restrained, allowing for intermediate anchors and far fewer guides to be used. These designs are extremely helpful when designing with space or structural limitations, as well as with load limitations on piping and equipment. Common features and benefits of expansion joints are achieved, and the economic benefit of this approach includes far fewer anchors and guides, resulting in an even smaller footprint greater energy efficiency, and reduced construction costs. We have several restrained designs to review. The first is the universal tied rubber expansion joint. Universal tied rubber expansion joints are designed to primarily absorb lateral and angular movement. The arrangement consists of tied devices attached to the expansion joint's external or internal hardware, and it is designed to restrain the full pressure thrust force of the system. Functionally, the axial movement of the long length of pipe is accepted as lateral movement in the adjacent pipe run and at the expansion joint, as can be seen in this illustration. Hinged expansion joints are designed to permit angular rotation in one plane. The arrangement consists of a pair of hinge plates connected with pins and attached to the expansion joint's external or internal hardware and designed to restrain the full pressure thrust forces. Hinged expansion joints can be used in sets of 2, as shown here, or 3 to absorb lateral movements in one plane. Again, functionally, the axial movement of the long length of pipe is accepted as lateral movement in the adjacent pipe. The two hinged joints work together with a center spool piece to accept this lateral movement. Gimbal restrained rubber expansion joints. Gimbal expansion joints are designed to permit angular rotation in multiple planes. The arrangement consists of 2 pairs of hinge plates connected with pins to a common gimbal ring and attached to the expansion joint's external or internal hardware. Designed to restrain the full pressure thrust force, gimbal expansion joints can be used in sets of 2 or sets of 2 with a single hinge design to absorb lateral movement in multiple planes. So once again, functionally, the axial movement of the long length of pipe is accepted as lateral movement in the adjacent pipe. The 2 gimbal joints work together with a center spool piece to accept this lateral movement. This time, the lateral movement is coming from 2 different planes. Inline pressure balanced. Inline pressure balanced expansion joints are the only effective solution for directly absorbing large axial movement while continually self-restraining the pressure thrust force. This arrangement consists of tied devices interconnecting its main joint section to its opposing balancing joint section. The balancing joint section needs to have twice the effective thrust area as the main joint section in order to balance the arrangement and to provide a kind of internal anchor. This point will be made clearer with the animation slide to follow. They are commonly used when the support structure or adjacent equipment have load limitations and no change of pipe direction can be utilized. So here you can see the center balancing joint section with its larger diameter, and it is moving opposite that of the main joint section. Together they accept direct axial movement while self-restraining the pressure thrust force. Elbow pressure balanced rubber expansion joints are designed to absorb all directional pipe movement while continually self-restraining the pressure thrust forces. This arrangement consists of tied devices interconnecting its main joint section to its opposing balancing joint section and functioning in an elbow configuration. The balancing joint section need only to have the same effective thrust area as the main joint section because the center T-fitting provides for a kind of internal anchor. These expansion joints are commonly used when the support structure and adjacent equipment have load limitations and a change in pipe direction can be utilized. So here you can see the balancing joint section with its similar diameter, and it is moving opposite that of the main joint section. Together they accept axial movement while self-restraining the pressure thrust forces. Dismantling expansion joints are designed for self-retraction to facilitate access to piping and equipment, as well as for unmatched ease of installation and subsequent removal due to its pre-compressed capability. Additionally, they function as universal tied rubber expansion joints and can absorb axial, lateral, and angular pipe movements. The illustration to the left is of the pre-compression illustration, and the illustration to the right shows self-retraction. The animation here is showing self-retraction. You remove the attachment hardware of the adjacent equipment and self-retract the dismantling joint with its control units. So some system design and optimization conclusions. Performance rubber expansion joints, both unrestrained and restrained, can play a significant role in designing an optimal piping system. Each expansion joint arrangement possesses unique characteristics which make it particularly suitable for a given application. In many cases, multiple solutions are possible, allowing for an owner's preference, and qualified manufacturers are available for further consultation and design review. That ends our first section on rubber expansion joints, basic applications to advanced solutions. It was on system design and optimization. The second part will be on system reliability and efficiency. Thank you very much.